All right, well, thank you, Matt. Thank you for the entire team for giving me the opportunity to present. As Matt mentioned, I'm Craig Schlenoff. I'm the program manager for NIST Measurement Science for Manufacturing Robotics program. Recently, I took over at the beginning of this year, also a group leader at NIST. So my presentation is going to be a little bit higher level than some of the ones that you've seen up to now. I'm going to start by giving just kind of a general overview of some of the things that we're doing at NIST and Robotics and show how ROS and ROS Industrial is fitting in. And then I'm going to dive a little bit deeper into the area of robot agility, which Matt kind of primed us on at the beginning of this workshop. So just a kind of a big picture. What right now, if you look at robots, and I imagine I'm preaching to the choir for this, is that a very small percentage of potential users are benefiting from robots due to many reasons, and some of those reasons are ad hoc, expensive custom solutions for installation, fixturing, and tooling, lengthy programming for each new part, limited to no tasking, replanning, or agility, and separated from humans for safety and cannot collaborate or assist. So this is close to the state of the art where we are now. And where we want to get to, I think where this probably everybody in this workshop wants to get to, is advances in robotics enable the future vision of greater responsiveness, productivity, higher quality with collaborative robots that's achievable by small and medium and large manufacturers. We're looking at the whole gamut of manufacturers. So NIST, and by the way, if you're not familiar with NIST, NIST is the National Institute of Standards and Technology. We're part of the Department of Commerce in the U.S. government. And what we do to try to enable this vision is we try to develop metrics, protocols, benchmarks, models, test beds, standards, things of that sort to get us from the left-hand side over to the right-hand side. So that's why we're here. That's what your taxpayers are paying for, and that's what we try to do. What we did is we structured our program around what we see as the core challenges facing robotics. And each one of those yellow boxes that you see on your screen is a project and is one of those challenges. So I'm going to very briefly describe them, and then shortly after this, I'm going to talk about the agility aspect. Starting at the top left, perception is obviously a big challenge in robotics. So we have a perception performance robotic systems whose goal is to assess and assure sensors and perception systems. What we're doing is measuring the perception systems, characterizing how well they perform. So the end user will know, what they're capable of and if they're capable of doing what they need to have done. Going down, grasping, manipulation, and safety performance. So this is really primarily the grasping and manipulation side. And again, assessing and assuring. You'll keep on seeing assessing and assuring for work that we do because that's in line with the NIST mission. Dexterous grasping and contact safety. So when you pick something up, how much force does it put on it? How well can it grasp it? How well can it figure out the grasp points and things of that sort? We have mobility performance of robotic systems. So this is the whole mobility side where we're assessing and assuring of the vehicle itself, like an AGV on the shop floor, mobile manipulators, and wearables. More recently, we've been doing some work with wearables, so exoskeletons, and being able to characterize the performance of those exoskeletons to allow the user to do whatever job they need to do. But in addition, we're doing mobile manipulation and AGVs as well. Going to the top right, we have an embodied AI and data generation for manufacturing. So AI seems to be the buzzword these days, and we have a project that's focused on that. What we're doing primarily is focusing on the data generation side and gathering data to help in training AI systems for manufacturing robotics. So not only gathering data, but trying to characterize the data, understanding if the data is biased, understanding how much data is needed in order to accomplish a certain task, what the format of that data should be, how accurate that data should be, things of that sort. So this is all part of our embodied AI and data generation project. The next one down is agility performance of robotic systems. And so I'm going to talk a lot more about this throughout the presentation, but this project is focusing on, and this is very well aligned with some of the stuff that I think ROS and ROS Industrial helps to provide, is to be able to easily and rapidly reconfigure and retask robots. So this is looking very much at the software side as opposed to the hardware side. So we want to understand how we can more quickly program robots to perform a new task as it's presented to them. We want to find out how the robot can better sense the environment and understand, for example, where things fail and be able to recover from those failures. And I'm going to talk a lot more about that, but that's a very tough challenge, and there's a lot that goes into that, and we'll talk about what that takes. The bottom right, performance of human-robot interaction. This is not only human-robot, but also robot-robot interaction, and it's providing the foundations for intuitive and effective interaction methods. So how can a human and a robot work together? How can we use VR and AR types of technologies to allow for better interface between robots? How can robots work well together and synchronize their actions, things of that sort? And then the bottom is tools for collaborative robots. And so this is really focusing on small and medium-sized enterprises, small companies that typically maybe aren't considering using robots because of the large upfront costs and large upfront time it takes to get the robots up and running. And we're trying to characterize what are the challenges that they're facing in using robots and putting together tools that would allow them to more quickly get those robots up to speed, things like calibration techniques and registration techniques and things of that sort. So that's an overview. I do want to talk briefly about how we're using ROS in some of these projects. So the first one here, the grasping and manipulation project, the project is currently in the process of porting most of the test bed to ROS so that they can better leverage outside work when developing the test methods for robot assembly, again, focusing on robot assembly. And some of the equipment that's being ported to ROS includes the Franca Amica Panda arm, the KUKA EWA 7-kilogram arm, the Robotic 3-finger gripper, and the shunt dexterous hand. So those are some of the robots that we have in the lab, and they're in the process of actively porting those to ROS. For the second project, the mobility project, they're using ROS primarily for tech transfer, and they're doing this under a grant that they have with Marquette. It's for dynamic measurement of mobile manipulator performance, and they're using ROS to leverage its navigation libraries and the Move It library to control the UR5 manipulator on a Pioneer LX mobile base. And they're using Gazebo as well in order to do some simulations. For the human-robot interaction project, ROS is a low-level command interface for 2 of their robots, and they're exploring multiple avenues to integrate, emulate ROS into their entire test bed. So there's active work being going on in ROS there. And the agility project, I'm going to talk about a lot more and how we're using ROS in the subsequent slides, but it's also being used there. There's another robotics effort that doesn't fall under the realm of manufacturing. So this is our manufacturing program. There's one that's focusing on first responders in the Department of Homeland Security. They also are using ROS in their efforts, and they're using ROS to control a Telemax robot with an arm on it, as well as a 360-degree camera and an RGBD sensor through Unity using a VR headset. So what I mainly wanted to bring across in this slide is that ROS shows up everywhere, almost everywhere in the projects that we have in NIST, and we rely very heavily upon it. Some of the things that NIST provides, so starting at the top left, we have various test methods and metrics. So this is a test method that's looking at the amount of force that we can limit the robot from putting on an object and being able to measure those force and measuring the grasps. The bottom left is some test methods that we put together for our exoskeleton work. In the middle, we have various artifacts that we provide. So I mentioned before the work that we did for robot-robot interaction. And this is a 2-armed robot, a Baxter robot, that's trying to lift that bar by coordinating the motion of the 2 arms. And that bar is instrumented with stress and strain gauges, so we can see how well it can lift the bar at exactly the same pace. And on the right-hand side, we have work that I'm going to describe where we deal with various competitions. Area I'm going to talk about a little bit, and we also provide software tools. So that's kind of an overview of some of the things that we do in NIST. So I want to spend the rest of this talking about robot agility. So we're very excited about the area of robot agility. As Matt mentioned earlier, we're going to be working closely with SWIRI through a grant in order to start tackling some of the issues that I'm mentioning here, and we're very excited to be working with SWIRI. So when we talk about robot agility, we're really focusing more on the software side as opposed to the hardware side. So things such as how can a robot be quickly tasked to perform an operation? How well can a robot adapt and respond to task failures? How well can it replan when a new goal was provided to it? How can we allow for interchangeability of robots and things of that sort? So we're trying to get the robot to be smarter, for lack of a better term. I have to be careful when I tell my kids that because they think the robots are going to take over the world. I tell them that that's not going to happen. But that's really what we're trying to do, is we're trying to get the robots to be smarter so they can be more agile and they can plan and deal with things such as failures and things of that sort. So we focused on this areas it was very clear that we needed to focus on this area. So we reviewed roadmaps and numerous site visits and went to conferences and discussions and standards groups, and we kept on hearing the same things over and over and over again. That robots take a long time to program, that they're incapable of adapting to changing environments, that once a company decides on a robot brand, they're tied to that brand because of the cost of the large infrastructural cost, and training a robot to perform a new task is very time consuming and not cost effective unless you have a very large lot size. So again, preaching to the choir for this, these are challenges that we know exist and things that we're trying to address. There will not be a quiz on the slide, but what we did is we went through and we tried to get our hands around what would it take to get a robot to be agile. And so we put together this block diagram. I'm not going to go through it in detail. I just want to highlight a few parts. The purple box at the bottom left there that says ontology in it, one of the first things we recognize is that for a robot to be able to be agile, it's got to know stuff about the environment. It's got to know what's in the environment. It's got to be able to recognize it. It's got to know characteristics of it. It's got to know what's going on around it. No different than a 2-year-old. If a 2-year-old is trying to be agile and do something, it's got to have enough information about what's in the environment to be able to do that. And so we've done some work in developing ontologies, and I'll talk about that in a minute. The robot also needs to understand itself. It needs to understand how far it can reach, how heavy of something it can lift, all information about itself so it knows what it can do. So if something fails, it's got to know what its capabilities are to be able to correct whatever failed. That's the red box at the top left. The bluish box there, the light blue box, is it needs to be able to plan. So once it knows about itself, once it knows about the environment, it's got to take that information and make a plan to be able to address whatever comes up, whether it be a new goal or an error or whatever it happens to be. It's got to be able to plan. And ideally, we want it to plan in such a way that it can work with other robots. The other robots that maybe have different underlying programming languages or different ways of doing things or different degrees of freedom, but still be able to work with them to accomplish the task. And lastly is that orange box, and that orange box is the test method. So once we do all this, how do we know how agile a robot really is? How do we know what makes sense? And so, or how do we measure it? And so there needs to be metrics to do that. The rest of this presentation, I'm just going to talk about these 4 boxes. So the first thing that we did is that first box is talking about understanding the environment. We work with IEEE in order to develop an ontology called Core Ontologies for Robotics and Automation. This was standardized and published in 2015. It became, and there was a number of, obviously for years before that, it took work in order to get that standard together. We had 175 members representing 23 countries that came together in order to develop the standard, about half from education, 25% from industry, 25% from government, about half US and half non-US. And it got all kinds of recognition. I won't go through this in detail, but it was mentioned in former President Obama's National Artificial Intelligence Research and Development strategic document, and nice awards from IEEE, and purchased over 2,100 times, and so forth and so on. So if anybody wants some more information on this, I'm happy to make it available. There's a number of working groups that have been building down from this and developing more specialized ontologies based upon this higher level ontology. This is actually one of my favorite videos, and courtesy of GTRI, Georgia Tech Research Institute, who we work with. I think they're actually going to be presenting next, so hopefully I'm not taking away Steve's thunder. But one of the things that we wanted to do is to be able to characterize how a robot can understand its own capabilities. And so this video shows this, I don't know if you can see my mouse, but it's this silver bar that's at the bottom there. And the robot needs to pick up the bar, but the problem is it can't pick up the bar because it can't reach the center of gravity. And so what it's doing is it's got to figure out how to get to the center of gravity so it doesn't pick it up from the side and tilt it over and have it drop out of the gripper. And the robot is smart enough in order to slide the bar over so that it can reach the center of gravity, move over, pick it up from the center of gravity of the bar, and then move it beside itself. And so I think anybody can look at this and say, of course, that makes sense. That's what you should do. I mean, anybody would know how to do that. But if you think of the knowledge that the robot has to have in order to do that, it's got to know how much the bar weighs. It's got to know how far it can reach. It's got to know where the center of gravity is. It's got to know how heavy of something it can pick up. It's got to know that it can slide the object. The knowledge is immense. And even though we take it for granted, and planning that knowledge into the robot is very challenging, and there's a lot that goes into that. And so that's part of why this knowledge representation is so important. The third part I wanted to talk about was planning. So one of the things that we've done is develop something called the Canonical Robot Command Language, and it's a messaging language for sending commands to and receiving status from a robot end effector. And it provides a neutral way of representing these commands independent of the underlying robot programming language. We actually map it to the underlying to the robot, but the planning itself is done at a higher level in CRCL. If you're interested in something like this, and if you're interested in CRCL, it actually is released as part of the ROS industrial release package, and it's currently available out there. So there's a part of the GitHub, there's a place to get to it, and if you can't find it, I'm happy to share that with you. What's shown here is 2 different robots performing similar types of operations using the exact same specification represented in CRCL, but one mapped to the FANUC and one mapped to the Cuckoo robot. So we only had to specify what we wanted it to do once. And probably preaching to the choir here again, but this is the underlying code for the FANUC that uses Carol, and for the Modaman, which uses Inform. Same task, fundamentally different way of representing the knowledge, which is the challenge of having these robots work closely together. I know we're running late, so I'm going to skip this. This is just a video, and I can make this available afterwards of how we put all these things together to get it to work. But for the interest of time, I'm going to skip over this. One thing I do want to mention is that we are one of the things that we're doing is, in order to be able to prove some of the things that we just showed, in addition to the video that I just skipped over, is we have some assembly task boards that we've put together. This is some of the videos of the task boards, but these task boards are set up so that we have some of the challenges that are facing industry. So if you look at the very top left, there's examples of the task boards that have plugs and cables that wind around things and wires and all kinds of stuff. And the goal is to manipulate those task boards in order to move things around and put them in different configurations or take them out and put them back in. And so this is some of the things that we're moving towards using to test the agility of systems, to see how well we can use some of these technologies in order to manipulate those task boards. In the last few minutes, I do want to talk about ARIAC. So ARIAC is a competition, a virtual competition that we run every year. Its goal is to test the agility of industrial robot systems, with the goal of enabling industrial robots on the shop floor to be more productive, autonomous, and to require less time from shop floor workers. You probably recognize the simulation engine. This is Gazebo. We use Gazebo and ROS in order to run the simulation and to run the competition. This is the 5th year of our competition. It's just about to get started. It is a prize competition, so we've set that $10,000 for first prize, $5,000 for second prize, and $2,500 for third prize. The goal here is, what we do is we work with industry to not only represent the environment, but represent the challenges that they're facing with respect to robot agility. So things such as parts dropping out of the gripper, or sensors going out, or processes being changed in the middle of another process happening, and things of that sort. This is what we've heard from industry, and we've modeled these within the simulation environment. And then teams come in and develop control systems to control the robots to accomplish some goal in the presence of these challenges. And so this is what they do. We typically have about 50 to 60 teams register each year. Last year was a huge year. We had 110 teams register. We have finals, and the finals, we usually have about 4 to 6 teams that make it to the finals. And so this year's competition is actually happening next month. So if you're interested, it may be a little bit late, even though you can do it if you rush, but we have this every year. So if you're interested in participating in this, let me know. This is very tied to Gazebo and ROS, as I mentioned. So I think I mentioned a lot of things in the slide already, but here's some examples of the ROS topics that we use and ROS services in order to make available to the team. So things like retrieving orders and querying the storage locations of parts, querying sensors, controlling the arm, controlling the vacuum gripper, things of that sort, are all ROS interfaces, and these ROS interfaces are what the teams use and interface with in order to control the robots in the simulated environment. All right, did my best to stay on time. I think I was within a minute. So I will leave it at that. I don't certainly want to cut into lunch any more than I have to, but if this time I can answer questions.